Hello viewers, welcome to our second lesson on linear programming. In the first lesson, we introduced you to the idea of what linear programming is, and we also learned how to formulate a linear programming problem. Let us begin with a quick review of what linear programming problem is, and then look at the results which will help us to find the solution of a linear programming problem, and then take the two problems that were described last time and solve them graphically. So, hopefully, you are ready to follow today's lesson. Linear programming problem, what is it? It is a process of finding the optimal value of a linear function of several variables. The linear function is called objective function, subject to the conditions that the variables are non-negative and satisfy a set of linear inequalities which are the constraints. There are two major theorems that work to give us the solution of a linear programming problem, and they are of course stated without proof in your textbooks. Theorem 1 says that if R is a feasible region for a linear programming problem and z equal to ax plus by be the objective function, then z has an optimal value, maximum or minimum, where the variables x and y are subject to constraints described by linear inequalities, then this optimal value must occur at a corner point known as also the vertex of the feasible region. Second theorem says that if R is the feasible region for a linear programming problem and z equal to ax plus by be the objective function, and if this region R is bounded, then the objective function z has both a maximum and a minimum value on R, and each of these occurs at a corner point of the region R. But if the region is unbounded, then a maximum or a minimum may not exist. However, if it exists, it must occur only at a corner point of R. Now, what this two theorem talk about is the corner point. So, the method, graphical method that we are going to employ to solve linear programming problem is known as a corner point method. What do we do in this corner point method? We find the feasible region first, and then we identify the corner points of the feasible region. Here is a stepwise description of this method. What we need to do is start with finding feasible region. Feasible region is a region which is satisfying all the constraints which were linear inequalities. So, feasible region is nothing but the common region of the Cartesian system where all the inequalities and of course, the non-negative restrictions are being satisfied. And then we will find the corner points, that is the vertices of this feasible region. Next, we will evaluate the objective function at each of these corner points, and if capital M and small m respectively be the largest and the smallest value of these points, then if the feasible region is bounded, then capital M and small m respectively are the maximum and minimum values of the objective function. If feasible region is unbounded, then a little more care. Capital M is the maximum value of the objective function if the open half plane determined by the inequality ax plus by greater than m has no point in common with the feasible region. Otherwise, the objective function has no maximum value. Now, similar condition holds good for minimum. So, if small m is the minimum value of the objective function, we have to go another extra step to decide if this is the minimum value. So, for that we consider the open half plane represented by Ax plus By is less than lowercase m, and make sure that it has no point in common with the feasible region. Otherwise, the objective function has no minimum value. Now, theoretically these look very complex theorems. So, the best would be to take a problem, formulate and then solve it. I am taking the same problems that we discussed in our last lesson. So, the problems were discussed in terms of how to formulate. Today our focus would be how to solve. The first problem is from your NCERT book, question number 4, page 526. And we saw that here the linear programming problem, the model turned out to be I have to maximize z, which is 7.50 times x plus 5y, subject to the constraint which simplified to be 2x plus y is less than equal to 60, x is less than equal to 20, 2x plus 3y is less than equal to 120, and non-negative restrictions x and y both greater than equal to 0, where x is the number of type A toys and y represents the number of type B toys that we are looking at producing or manufacturing. To decide the feasible region, we start with of course a graph paper and choose suitable scale, so that you can represent all the 3 linear or more constraints that may be part of the problem in a proper fashion. In this case, I start with first the straight line. So, to mark the region, I must have the straight line. So, I first plot the straight line representing 2x plus y equal to 60 and then plot the other 2 lines in this case, that is x equal to 20, vertical line, 2x plus 3y equal to 120. To decide the feasible region, recall what you learned in grade 11. How do I decide the region which represents the solution region of a linear inequality? Every line will divide the entire Cartesian system into 2 planes. In this picture right now, if I am looking at the placement of origin, then none of these lines pass through origin. So, I would call one half plane to be a half plane which contains origin and the other which does not contain origin. We want to decide where is the shading going to be. So, 0, 0 becomes a testing point for us. If you put x equal to 0 and y equal to 0 in your first inequality, which is say 2x plus y less than equal to 60, do you think 0, 0 satisfies it? Yes. So, the shading will be the half plane which contains origin, whereas same thing is happening for the other 2 straight lines, which is if I take x equal to 20 and then I want to decide which side I am going to shade to represent x less than equal to 20, then origin does satisfy it. Similarly, 2x plus 3y less than equal to 120 is satisfied by 0, 0. So, the solution region for all the 3 inequalities is the half plane which contains origin for the respective lines. The common feasible region would be the one where all the 3 are intersecting. At the same time, I also have to consider the non-negative restrictions, that is x and y greater than equal to 0. Therefore, the common feasible solution region that I am looking at gets restricted to the first quadrant. So, here we have a bounded region which represents the feasible solution for the problem which had the constraints 2x plus y less than equal to 60, x less than equal to 20, 2x plus 3y less than equal to 120 and x and y greater than equal to 0. So, as in this figure, the shaded region is the feasible region. Corner point method says that find the corner points of the bounded or the feasible region. In this case, what are the corner points? You can either read most of them from the graph, but if there is a point which is not very clearly labeled from the graph, then solve the 2 linear equations the straight lines, the two straight lines which are intersecting to give rise to that corner point, solve their equation simultaneously and get the corner points. In this problem, I have 5 corner points. What the method requires now is that you evaluate the objective function at these corner points. That means, I will now evaluate z, which is 7.50 x plus 5 y at all the 5 corner points. Do you see if this function is taking a certain maximum value at a particular point? Surely it is. It is taking a maximum value of 262.50 at the corner point 15, 30. And that is how you decide what the conclusion is going to be. We therefore, from here say that for maximum profit, 15 toys of type A and 30 toys of type B should be manufactured. And if the problem also says also find the maximum profit, then the maximum profit is going to be rupees 262.50. It's as simple as this, and therefore, I think you would enjoy trying out another problem. So, here's our next problem. It's again the same question which we discussed in our previous lesson in terms of how to formulate the LPP. Today, we are going to solve it as well. This is question number 10 from page 520 of NCERT book. The problem states there are two types of fertilizers, F1 and F2. F1 consists of 10% nitrogen, 6% phosphoric acid, and F2 consists of 5% nitrogen and 10% phosphoric acid. After testing the soil conditions, a farmer finds that she needs at least 14 kg of nitrogen and 14 kg of phosphoric acid for her crop. If F1 costs rupees 6 per kg and F2 costs rupees 5 per kg, determine how much of each type of fertilizer should be used so that the nutrient requirements are met at a minimum cost. Also, what is the minimum cost? Now, this is a problem which we had discussed in detail, where we start with x kgs to be the amount bought for fertilizer F1, y of fertilizer F2. You may translate this information in a tabular form so that you can interpret these conditions as an LPP with ease. So, we need to minimize the cost z, which is 6x plus 5y, subject to the constraints which simplified after I translate 10% of x plus 5% of y to be same as 2x plus y is greater than equal to 280, and then 6% of x plus 10% of y to be greater than equal to 14 translates to be 3x plus 5y is greater than equal to 700, and non-negative restrictions, very, very important, x and y both should be greater than equal to 0. Let us now start looking at the graphical solution of this. To begin with, we will plot the feasible region which will be represented by the constraints and the non-negative restriction. I am sure you will enjoy shading, getting the region for 2x plus y greater than equal to 280 and 3x plus 5y greater than equal to 700. Starting with first plotting the straight line, check whether origin satisfies the inequality 2x plus y greater than equal to 280 or not. In this case, it does not. So, the shading will be the half plane which does not contain origin. Similarly, you may try doing the same exercise for the second inequality, that is for 3x plus 5y greater than equal to 700. Plot the straight line first in the same graph and then decide the solution region, and then look at where do the two shadings overlap. At the same time, think about the non-negative restrictions. So, your feasible region will be limited to the first quadrant, and therefore, the shading will look like, the region would look like an unbounded region bounded from the lower side. In this case, the vertices, if we find the points of intersection of the two straight lines and as well as where these lines meet the x and y axis, I am looking at 3 vertices of this feasible region A, B and C. These are our corner points, and we test the objective function at these corner points. So, we find the value of z, which is 6x plus 5y. In this case, it is giving us the minimum value of 1000 at B, which is 100, 80. So, going by our previous method, 1000 would be the minimum cost at x equal to 100 and y equal to 80. But if you had noticed the theorem 2 that we discussed, it said if the region is unbounded, then an extra step to be considered. What is that? You will now shade the half plane, that is 6x plus 5y less than 1000 to decide if 1000 is the minimum cost. That is, plot 6x plus 5y less than 1000, taking the care that when you talk about less than 1000, not greater than or equal to, your line will be a dashed line. Region in this case would be the half plane which contains origin. So, very clearly the two regions are not meeting at any common point. That confirms that the cost of 1000 rupees that we have evaluated at point B is the minimum cost, and therefore, we are ready with our conclusion, which says that 100 kg of fertilizer F1 and 80 kg of fertilizer F2 should be used so that nutrient requirements are met at a minimal cost. And what is the minimum cost? Rupees 1000. I think with these two problems, one on minimization and the other on maximization, you have got a fair idea of how to solve a linear programming problem. But there are still few more details that we need to investigate. So, we will meet again next time with some more problems on linear programming, and hope you will be there to follow and practice those and few more with us. Till then, all the best.